So in this part of the video, we'll talk about barometer. So barometer is a device that is used to measure pressure, or rather atmospheric pressure. Okay, so let's draw a very simple barometer. So let us consider, let's just say I've taken a vessel and I have filled that vessel with mercury. I don't know if the red is the right color to represent mercury, but I have done it. So this is mercury, and now I'll be dipping a test tube in the mercury. Alright, so here's something that you need to understand. Alright, so ideally speaking, while this test tube is dipped, okay, ideally speaking, when this test tube is dipped, the pressure inside the test tube needs to be zero, which basically means that there should be no gas present inside test tube, which is practically a little impossible. Therefore, some or the other gas might get trapped, but ideally speaking, again, there should not be any gas inside the test tube while you are inserting the test tube in the mercury. Now, while it is getting placed inside the mercury, the pressure in this particular region, let's just say in this particular region is atmospheric pressure. The pressure at this particular region is zero because there is vacuum. Okay, so pressure at vacuum is basically zero. All right, and here there is 1 atm pressure if you are taking sea level at both these region. So you can observe that there is pressure difference inside the test tube and outside the test tube. Now, since there is pressure difference inside the test tube and outside the test tube, this pressure difference would get nullified as soon as I dip the test tube inside the mercury. What will happen is the mercury will start flowing inside the test tube in order to nullify the pressure difference. Alright, so let me draw another diagram just to explain the whole phenomena. So let's just I've taken a vessel, I've filled it with some red colored mercury. By the way, mercury is not red, I'm just representing it with the red color. Now if I have dipped the test tube, the mercury will rush inside the test tube, and we will see a rise in the mercury column of some height h. Alright, so the rush of the mercury inside the vessel is due to the pressure difference inside the test tube and outside the test tube. Okay, so the pressure outside is 1 atm and inside is 0, and because of which the mercury is rushed inside the test tube, and I can observe later on that there is a height of h height of mercury h that is being observed. All right, now let's apply the rules that we studied in the previous page. All right, here now let's me write some points. Let's write A, B and C. Alright, okay, I hope my diagrams are clear. I'm not very good at drawing diagrams, but I hope it's tolerable enough. Alright, so pressure at point A is equal to pressure at point B. Why is that so? Because pressure at along the same horizontal line is equal, and pressure at point C will be equal to 0. Why? Because ideally there is no gas trapped in this particular column, although it is highly unlikely, because while you're inserting, some gas will definitely get trapped in this particular space. So now in this particular diagram I have considered that there is vacuum. Alright, so I will say that the pressure at point C will be 0. Now I need to compute the pressure at point B. Alright, so I will say that Okay, let's just say first point is pressure at point A will be atmospheric pressure. Okay, so pressure at point B will be atmospheric pressure. Secondly, pressure at point B will be pressure at point C plus the pressure due to the liquid of height h will be equal to rho. Rho of which liquid? Mercury, multiplied by h multiplied by acceleration due to gravity. Alright, this is the pressure of pressure at point B due to the liquid column of mercury. Alright, so pressure at point C is 0. Now I'll get pressure at point B equal to some rho gh. Alright, rho gh, and pressure at point B is equal to atmospheric pressure, because pressure at point A is equal to pressure at point B, and pressure at point A is atmospheric pressure. I will say that pressure at point B is P atm. So you might have heard that 1 atm is nothing but 76 centimeter of mercury. Alright, so what does this really mean? It means that the height that I'm obtaining in this particular liquid column will be equal to 76 centimeter. So why I need to define 76 centimeter of Hg? The reason I need to define the liquid as well, because the density of mercury is also fixed. So as soon as I say these two information, the height of the liquid column and the type of liquid, I can immediately calculate the pressure, which is density of the liquid multiplied by acceleration due to gravity multiplied by the height. So pressure can be defined in terms of the type of liquid and the height of the liquid column. Alright, so this is the pressure due to atmosphere. So the longer the height of the mercury of the liquid column, more will be the atmospheric pressure. Alright, now let us replace this particular liquid with water and let's see what would happen. Alright, so I have taken the same setup. Let's take the same setup, and now I am filling the liquid column with water. Okay, so water can be represented as blue itself. Right, although the color of water is not blue. So now I've inverted a test tube, and as soon as I invert the test tube inside the liquid column, there will be a rise in the water. Okay, so the rise is of height h again. So now we know that P atmosphere, okay, atmospheric pressure is equal to density of mercury into acceleration due to gravity multiply height of mercury. Now this will also be equal to density of water, because in this case there will be some force applied by the atmosphere on the liquid, and because of this force being applied on the liquid, there will be a push of water or the rush of water getting inside the test tube. Okay, so I can express PATM also as density of water multiplied by G multiplied the height of water. Now this two atmospheric pressure obviously will be same irrespective of the liquid, so obviously I can say that these two values will be equal. Alright, so let's equate them. Density of mercury multiplied by G multiplied by height of mercury will be equal to density of water multiplied by G multiplied by height of water. Now G will cancel out. Density of water is, I can take it as 13.6. So density of mercury, I'll write it down as 13.6 gram per centimeter cube. Alright, so I'm just going to make it as 13.6 multiplied by the height of mercury. The height of mercury, if I have to calculate in centimeter, it will be equal to 76 centimeter. all right, equal to density of water. Density of water is actually, if you already know, it is 1 gram per centimeter cube at 4 degrees Celsius. So we'll take it as 1 itself for easier calculation, multiplied by height of water. So if you calculate height of water, it will come out to be 1033 approximately centimeter. This is an approx answer, by the way. Okay, now let's understand what does this answer mean. All right, so height of water is coming out to be 1033 centimeter. This is roughly equal to 10.3 meters. All right, so if I, instead of mercury, if I use water as for measuring atmospheric pressure, I would require a test tube of at least 10.33 meters, because that will be the rise in water. So because water is a very lighter liquid, okay, compared to mercury, there will be a very high rise in height, okay, because you can see the atmospheric pressure is not changing, but the atmospheric so the pressure exerted by the atmosphere will create a much higher height of water in order to compensate this particular force. Whereas if I take a heavier liquid like mercury, the rise in height will be much less. So if I could have taken a very hypothetical liquid, because mercury is having the highest density among all the liquids, but if I take a hypothetical liquid of a higher density, I will observe a much smaller height. Okay, so it is preferable that you take a liquid which has a high density, because obviously you will require a smaller test tube. If you take a liquid of lower density, you will require a much longer size test tube. All right, so this is again a cost effectiveness thing. All right, so now let's talk about a very similar thing. Okay, so let's generalize this point also. So if I have let's just say density, a liquid of density rho 1, which has achieved a height 1 in the column, in the test tube column, and if I take another liquid of density rho of height 2, this will be the relation between them. Rho 1 H1 will be equal to rho 2 H2. All right, so this is basically this is only true when the pressure experienced by both these liquid are same. Okay, then I can say that rho 1 H1 is equal to rho 2 H2. So for example, if you are substituting mercury and you are substituting it with some liquid X whose density is rho X and height is Hx, I will just write that rho of Hg multiplied by height of Hg will be equal to rho of X multiplied by height of X. So this is the equation that I'll be forming if I replace mercury with any liquid X.